Hello, AP Physics 1 students. Alright, let's go back into our handwritten notes. So far, we've been looking at the magnetic field created by a wire with current, but the wire had to be long and straight. And while we have the equation for that, there are certainly other geometries. We're not really going to be dealing with the equation for this, but qualitatively, let's see what happens if instead we have a loop of wire. So this is a circular loop of wire, and there are charges flowing around in this general sort of direction. Here it goes. Okay. So this is like the closer side of the wire. There's the farther side. If you can imagine, we're looking at it from the side. And there's some imaginary source of voltage. I don't put the source of voltage on the picture just because it sort of muddies it up. Imagine there's a source of voltage forcing charges around this way. If we're looking at it from above, this would be the counterclockwise direction. Okay, so we should be able to figure out the direction of the field produced by that if we imagine just sections of the wire. So you should be able to see as you follow charges around, right here the charges are sort of coming out of the page towards you, and over here charges are moving away from you. You can visualize that, right? Going to the right and then away from you, that's the X, and then to the left, and then towards you, that's the dot. Okay, so if we isolate just this section of the wire here, go ahead and grab it with your right hand, because you know we're finding the field and we always grab the wire for that. Your thumb should be pointing out of the paper, and you should see that over here the field is pointing to the bottom of the page, and in the interior of the loop your fingers are pointing to the top of the page, right? So if you're grabbing the wire this way, your fingers are tracing out a circle like this, but all we care about is the field over here, the field over here. And you want to do the same thing for this section of the wire here, where the charge is moving directly away from you into the page. So go ahead and grab that section of the wire with your thumb pointing into the page, wrap your fingers around, right? And you should see that over here, your fingers are pointing to the bottom of the page. Over here, your fingers are pointing to the top of the page. Can you see that, right? Your fingers are tracing out, in this case, a clockwise pointing circle down over here, or to the bottom of the page, up, or to the top of the page here. And here's the part that's interesting, is that the interior of the loop, these field lines are sort of clustered together. When they're clustered together, pointing the same way, that means that they strengthen each other. Here they're relatively far apart, but here they're close together, and we know the density of the lines indicates the strength of the field. So with a bunch together, this forms a relatively strong field in the interior of the wire. And that's just for one loop of wire. What if we stack them? More and more and more of them. Now the field in the interior is going to be very strong because all of them contribute more and more field. And so we're going to have almost a uniform field pointing this way in the interior of the loops. These are relatively weak. They're relatively far away from the wire. But here they're close together. And so they form a stronger field inside. More than, right? Now you don't have to draw this, but here's the idea. If we have charges flowing around over and over, looped and looped around, they cluster the field lines together. That forms a very strong field inside, with field lines pointing all in the same general direction, and then they sort of loop around to the outside. Well, that looks like a bar magnet, doesn't it? With this end being north, this end being south. Field lines are coming out of the loops here. That's like the north pole of a magnet. They're going into the loops here, that's like a south pole. We've created what's called an electromagnet or a solenoid. We're using moving charges looped around many times to create the same effects as a bar magnet. So we're actually making the same magnetic field as a bar magnet even without magnetic materials. Again, don't bother drawing this picture. We've already had this picture. I was going to show you how to draw a solenoid in another slide. Now here's the right-hand rule for solenoids. It's sort of like a shortcut. Now immediately some students are not going to like this because they're going to get confused because it's the exact opposite of how we do right-hand rule for grabbing a wire. This time, your fingers follow the current and your thumb shows the direction of the field. So over here, if the charge is moving around this way, follow this way with your fingers, and then when you stick your thumb out, it should be pointing to the top of the page. Follow this way with your fingers, thumbs pointing to the top of the page. This is sort of like a nice little shortcut. Now, if you don't like this shortcut, because it's the exact reverse of our normal grabbing one, you can always just grab the wire, right? Grab the wire near you, grab the wire over here, grab it over there. And the important part, though, when we're dealing with solenoids or electromagnets or loops of wire, is we only care about the field in the interior. That's where the field lines cluster together. Right? We don't care about the field over here, it's too weak. We only care about this field in the interior of the loops. Okay, so let's see how to draw a solenoid or an electromagnet. We start by drawing the core. We got to wrap the wire around something. Leave yourself lots of space. We're drawing a pretty big picture here, right? So draw the core, and now I'm going to draw the source of voltage. And I'm going to extend the wire so it loops around the core. And then it loops around, loops around, loops around, loops around a bunch of times. and then the wire continues over here and connects back to the batteries. All right, so now we have a completed circuit, and the first step is to trace the charges. We know that the long line here represents the positive terminal, and by conventional current, charges flow out of the positive terminal. They're going to flow up this way, so there's the charges moving to the top of the page. They're going to loop around and around and around, and let's draw the current in the near parts of the wire. Every single time the charges flow around, in these close parts of the wire, parts that are closest to us, the charges moving to the top of the page, they circle around the back, and they complete the circuit this way. And this is the part of the wire we're really concerned with, because it's the part closest to us. Okay, so now the point of this is we want to find the field in the interior of the loop, in the interior of the solenoid, because that's the only place where the field is really strong. The field lines are bunched together. So here you can do it the old way or the new way. So let's do the old way first. Let's grab any part of this wire that's close to us. And here again, use your imaginary wire as your pen or pencil, holding your left hand. With your right hand, your thumb is pointing at the top of the page. You're going to grab that wire, wrap your fingers around, but we want to stop when we get in the interior of the loop. We don't care about the field on the outside, we care about the field on the inside. And you should notice when you get to the field inside, your fingers are pointing this way to the left. Are you getting that? You should be, okay? Now, let's practice our right hand rule shortcut. This time, you're going to follow the charges with your fingers or your right hand. So your fingers are now pointing this way to the top of the page, and which way is your thumb pointing? Your thumb should be pointing to the left. Yeah, are you getting that? Okay, so the right hand rule shortcut or grabbing the wire, either way you can get the same thing. Some students like one, some students like the other, whichever works for you. But no matter what, you should be getting a field to the left. But these field lines are bunched together. Let's draw some more of them, right? More of these field lines are sort of coming out of this end. Field lines are coming in this way, and then we can show a field line sort of looping around, coming out of this end, looping around, coming out of this end, looping around, and now this field, this magnetic field, looks an awful lot like the field produced by a bar magnet. All that remains is to identify which end is north, which end is south. So we got the left side, the right side. Pause the video, identify which is the north pole of this electromagnet, which is the south pole. We know that field lines come out of north and go into south, and so this left side is the north pole, field lines are coming out. This side is the south pole, field lines are coming in. So again, here we have an electromagnet. All we have is charges moving around, looped around, looped around, looped around, and it forms the same sort of magnetic field as a bar magnet would, even without magnetic materials.